How's everyone doing? Did Tyler lead you astray? It was good. What's the verdict on our Monday lecture?
I will.
Come on, man.
I got stuck in the car.
Um,
I just transferred it yesterday.
okay. Yeah. Welcome. Yeah. I was in Florida for a workshop and I thought it was going to be warm and there's a tornado. So worse.
What part of Florida?
In Fort Lauderdale. Yeah, is like nice, is a tornado, but also nice. Warm tornado.
Usually that type of weather.
Yeah. Alrighty, let's get started. Welcome to lecture 4. Sorry I wasn't able to be here on Monday, but we will try and recap and make sure that everyone's up to speed before we go any further. So last class, we tried to cover Bayesian filtering, or at least most of it. How do we feel about Bayesian filtering? Not ready for Bayesian filtering? Okay. So we should, how do we feel about recapping Bayesian filtering some and then continuing? Yeah. Okay. Let's see. Let me wing it a little bit then. And let me see if we can work it out on.
Did you guys lecture on recorded?
It did get recorded, but it's good to just go over it.
What was it posted?
It got posted this morning. Yeah. So let me just go through the Bayesian filtering lecture. Wait. Okay, so no. There we go. All right. So to kind of recap, we started with last time I was lecturing, we were talking about the anatomy of a vehicle, and we started talking about state estimation, right? And we're saying, okay, state is telling you what things are changing in the world, like your position, your velocity, things like that. And we're trying to figure out how to estimate state accurately from our own motion and from sensor readings in the world, right? So the point of Bayesian filtering is that you want to have a probabilistic estimate of where your state is going to be in the world, right? So let's see, can we pull up? So the Bayesian filtering problem, right, is saying that, hey, you have some, sorry, people on Zoom, are you able to see everything? Yeah? Someone say something because I can't see you. Yeah. Okay, sweet. All right, so we want to figure out the state of the world, xt, right? So state could be things like where you are in the world, what your velocity is, what the math is, things like that, right? Some variable xt. And you want to do so from your history of observations, right? So let's say you're in a race car, your history of observations is going to be your laser scans in the world, right? And from your history of actions. So you're going to say, I don't know where I am. I had some belief of where I was at the start. And then I want to figure out where I am in the world by starting from my initial belief and then updating my belief as I get more and more information, right? And that information is both what actions I took, right? And what sensor readings I got. And so that's the problem. Filtering is just a fancy word for estimating where you are in the world, given your sensor readings and your action. Right? That's it. So the idea of filtering is because your sensors are noisy, your models are noisy, everything's a bit noisy. You need to be probabilistic. Otherwise, you want to actually, you don't want to be overconfident in the wrong way, right? So you want to estimate a density over where you are. And so that's the whole idea of state estimation. Right? Yeah.
Possible to minimize that.
Yes. Okay. So, all right. So, okay. So we can skip most of the probability stuff. The main things you need to remember are Bayes rule, right? So if you have x given y, you can write it in terms of P of y given x times P of x divided by P of y, right? And you also need to remember the like the rule for marginalization, which is saying that if you have let me write it on the iPad, you have, you know, P of A comma B, right? And you sum it up over A, that's going to be equal to P of B, right? So if you have a joint probability and you sum it up over one of the events, it's equal to the other, right? Those are the only two things we're going to use. Super easy. Yeah. Okay. So, so let's keep going. So the state estimation problem is saying you're going to see the student measurements. You want to estimate XT, given your current measurement and previous measurements and current action or all your previous actions, right? And so essentially we want to solve this problem. And the special assumption we're going to use in Bayesian filtering is the Markov assumption, right? The Markov assumption is just saying that the past is independent of the future, conditional on the present, right? So it means that if you know the current state of the world, you don't need to worry about the past. Right? And so it's saying that if I knew where I was, who cared where I was before? That's it, right? So what it's saying is that if I have this estimate, xt given zt, ut, and all the past x's, it's independent of all of the things in the past, conditional on the present, right? And so that's the main assumption that we're going to make use of, which is what we'd call the Markov assumption. Right? So it's saying that if you have a probability density of your current state, given your past states, right? Past states xt minus 1, xt minus 2, zt minus 1, zt minus 2, etc., you can reduce it to just depending on xt minus 1 and ut. Right? So if you want to have a shortcut to figure this out in graphs, right? All you need to think about is that, like you see the shaded circle in there, right? So if you try to like draw an arrow, you try to follow the arrows from ut to xt plus 1. If you have something shaded in between, that means it's independent, right? So you're saying that it's like if you have xt, then you no longer need stuff in the past, right? And that's the whole point of the Markov assumption. So all that it's going to allow us to do is to like represent these like things with lots of dependence on the past with just dependence on one step in the past, right? And then stuff that does for measurements, right? So you want to say, okay, your laser readings are only dependent on your current state and not on your past state, right? So where you are in the world will determine your laser readings, but it doesn't depend on anything else in the past, right? So that's all that the Markov property says. Yeah, everyone follows? Ask me questions. It's fine if we're going slow, no problem. Okay. So that's the idea of the Markov property. And so the Markov property says that, there are these two entities of interest, right? The first one is called the state transition model, the dynamics model, the motion model, right? Those are all different words for the same thing, but it's telling you how the world is changing, right? So if you knew what your past state was, xt minus 1, and you took an action ut, it tells you what the likelihood of xt is going to be, right? It's like if I was here, I took some action, where might I be at the next step, right? And then this is the measurement model, which is saying if I was at this position, right, what would the sensor readings be? So like, let's say I knew the map of the world, I was here, I shot some lasers out, like what is the likelihood that I would get that observation, right? And intuitively, this is going to say, okay, I was here right now, I took some action, where might I be in the future, right? So this is going to help you predict what's going to happen next, right? And what the sensor model is going to say, okay, I transition to another step. Now I take a sensor reading. It's going to help me make my belief of where I am more accurate. So imagine I was here, I transitioned to here, but my model wasn't perfect. So I had like high uncertainty over where I'm going to be. And then you get a sensor reading from the world, and that sensor reading can help reduce your uncertainty, right? Intuitively. And so the hope is that the measurement will help you be more precise, and then the motion model will help you move forward in time. Right? That's just the intuition of those two things. And so let's not worry about this for now. Did someone on Zoom say something? No. Okay. So the basic idea of Bayesian filtering, right, is that you want to estimate P of xt given ut xt minus 1, or here is that, sorry. given ut, zt, ut minus 1, zt minus 1, blah, 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 right? And so what we're going to try and do is break it up into two steps, right? One of the steps is going to say, let me try and express it, and let's call this thing our belief, right? We're going to try and break it up into two steps. Our first step is trying to propagate from the previous belief, right? So it's going to say, let's say I wanted the belief at time step t plus 1, right? I'm going to first go from the belief at time step t to something called the belief bar, right? And then the second step is going to say, I'm going to go from the belief bar at time step t plus 1 to the belief at time step t plus 1, right? And so what is the belief bar? The belief bar is going to be the probability, is going to be the probability that you're at some particular xt, given you took the action but not the measurement, okay? So like you were here, you took an action, right? So you incorporated the action, so you're at xt minus 1, you took the action ut, right? But you didn't incorporate the measurement at the next step. So you just took the action, and you have not incorporated the measurement. So this is going to be our zt. We did not incorporate the measurement, right? So the belief bar is going to be the probability of xt given ut and all the past u's and zt minus 1 and all the past c's. Yes? So it's just saying you want to estimate what your probability of your state is going to be when you took the action, but you did not incorporate the measurement. Yes? Imagine you move, and you're still waiting to take a measurement, and that's going to be your belief bar, right? And then the second step that you're going to do is you're going to, does it make sense to everyone? Okay. And then the second step you're going to do is, can I erase this? Okay, I can't erase this. Strange. Sorry, I'm having some technical difficulties here. Well, that's fine. The second step you're going to do is you're going to go from belief bar, right, which is saying p of xt given ut and all the past actions and zt minus 1 and all the past z's, right? And then you're going to incorporate the current measurement. So you're going to incorporate p of zt given xt, right? So the belief at time step t plus 1 is going to be the probability of xt given all of the past actions and all of the measurements, including the current measurement, right? So the only difference between belief and belief bar is whether you include the current measurement or not. That's it. Does that make sense? Right. So the way we're gonna solve this, I need to get rid of this. Sorry. The iPad always fails me. It's still on the screen. Sorry, 1 second. We're gonna restart the share. Okay, there we go. So, so the way we're gonna do it is we're gonna go from belief time step t to belief bar. Then we're gonna go from belief bar to the belief at the next time. Right? And so the first thing you're gonna do is you're gonna say that okay, you had your probabilities at your previous time step. So belief at time step xt minus 1, right? And then you're going to multiply it by your motion model. And then you're going to sum up over all possible things it could be in the past time step, right? So let's understand why that holds, right? So sorry, I need the iPad for this. 1 second. If I'm going over stuff that you guys already know, you should tell me now. And otherwise, I will keep going. Is this stuff all super clear, or should we still go over it? And would that be helpful? Helpful? Okay, great. Okay. So here's a way of thinking about it, right? So how do we actually, let's start again. I don't like to leave steps to black magic, right? So let's try and work out exactly why we're doing this. So we're saying, okay, we want belief bar, right, is equal to the p of xt given your current action and all your previous actions, right? till U1 and the previous measurements, right? This is the definition of belief bar, right? Now, by the law of total probability, right, you can say that, you have P of AB and you summed up A, it gives you P of B, right? By this rule, you can write this as P of xt minus 1 given ut to u1 and zt minus 1 to z1, right? Right, and then we're going to sum this up over xt minus 1, right? So it's just saying you literally apply this rule, right, to here. And so you're going to say you want the probability at your current time step. And so you can say that's like you take the joint over your current time step and your previous time step, and you sum it up over your previous time step, right? So by that rule, if you summed it up over A, the A disappears. Same way you're summing it up over xt minus 1, the xt minus 1 disappears. So these two things are just equivalent. Yes? No? Yes? No? Maybe? Thumbs up? All right, good. Okay, so this is equivalent, and then we're just gonna use a really simple property, which is the Markov property, right? Which is gonna say that you can write this joint probability, right, as P of xt given xt minus 1 ut times P of xt minus 1 given ut minus 1 and zt minus 1 summed up over xt minus 1, right? So all we did is when you have some joint probability, right? So you have P of A comma B, you can write it as P of A given B times P of B, right? And that's all we did. We said we had a joint probability, right? We wrote it as P of A, like let's call this thing A, let's call this thing B, right? So whereas P of A given B, and then we multiplied it times P of B, right? So what we did here is we took this xt minus 1, we moved the xt minus 1 to the other side of the bar, right? So you can think of this as A, this is B, P of A given B times P of B. Yes? So we're just using this, the definition of the joint probability, right? So let's kind of recap what we did, right? We started from belief bar, right? This is what we had called belief bar. Right, from belief bar, we added in this xt minus 1 and we summed up over xt minus 1. Yes. And then we said, okay, we're going to now write this joint probability as the conditional P of A given B times P of B. Right? That's it. Does that make sense? Okay. Now, all you need to, and I use the Markov property here because when you split this up, right, when you take xt minus 1 to the other side of the bar, it becomes independent of everything else in the past, right? Because you're saying that the current time step is independent of the past given the immediately previous time step. So xt is independent of everything else before given the current action and the previous xt minus 1. That's just the Markov property. So we started from belief bar, joint probability, split up the joint, use the Markov property, right? That's it. Yes.
Why is it UT minus 1 there, not UT?
Because your actions in the future cannot affect the past, right? And so it's just saying that you're independent of the future because you got your actions. Oh, that's a good question. Any other questions here? Okay, great. So what we've done is we've gone from belief bar to this thing. Now all you need to do is notice that this thing over here is just belief of xt minus 1, right? So if you look at the definition of belief, right? The definition of belief is just saying that this thing over here is just belief at xt minus 1, right? So what this all comes out to be then is it's just saying you're going to have sum of xt minus 1 of P of xt given xt minus 1 ut times belief at xt minus 1. Yes? You follow that? So start from belief bar, wrote out belief bar with the joint, separated the joint, used the Markov property, and then just looked at the form of one of the terms that just looks like belief xt minus one, right? And this like makes a lot of sense intuitively. Let's think about what this means. So belief xt minus one says, this is where I believe I might be, right? And so we're going to say that the likelihood that let's say I had a belief of where I might be, right? The likelihood I'm going to be at a particular point at the next time step is my belief that I might be at each individual point in the previous time step times the likelihood that that point brought me here, right? So it's like, okay, this point has some likelihood of bringing me here. This point has some likelihood of bringing me here. This point has some likelihood of bringing me here. I take my belief at each of those points, see what the likelihood is of bringing me to a particular point in the future, and I sum those up, right? So intuitively, it makes a lot of sense. It's just saying, take my past belief, measure how much the motion model is going to move me forward, and then just sum up over all possible places I could have been in the past, right? And that's going to tell me what is my belief over the future. How do we feel about that? Yes? Yeah.
We assuming that where we believe we were last step is the highest probability of like from the summation at the previous step kind of thing.
So you're not actually maximizing the probability, you're maintaining the entire belief of where you might be, right? So you're saying that, I don't know where I am, but this is my probability distribution of where I might be. So belief is not a number, it's a entire probability distribution.
Okay.
So you're maintaining your entire, when I say belief, I don't mean a single number. It's not saying that I am here. It's saying that I am here with this probability and here with this probability and here with this.
Okay.
Yeah.
So belief bar is on belief before we take the measurement.
Before we take it. So it's after you've taken an action, before you've taken the measure. Okay. Sweet. All right. So that is step one, and that's what we call prediction. For obvious reasons, you're here, you took an action, you want to predict where you might be. And the next step you're going to do is you're going to incorporate the measurement, right? So you're going to incorporate the measurement of your sensor, right? ZT at time step t. And then you're going to call that correction because you're correcting for what you got wrong, right? So the model is going to be wrong. You might have, oh man, is my iPad going to freak out again? Great. So you had some belief of where you were before or after you took an action, but that might be wrong. And a sensor reading can make it more accurate. So that's why it's called a correction step, right? So prediction moves you forward, correction corrects with the sensor reading. Yes. And so what this is saying is that, okay, belief bar told me P of xt given ut to u1 and zt minus 1 to z1, right? This is belief bar. Yes. And then what is belief at xt? It's going to be the probability of xt given ut to u1 and zt to z1. It's important to get the indexing right here, right? So this is, notice that this is zt minus 1 and this is zt, right? So the only difference is that you incorporated one extra measure, right? So this is belief and this is belief bar, right? And so we need to figure out how to go from belief bar to belief, right? And so it's going to be extremely simple. We're going to try and write out belief of xt, which is p of xt given ut to u1, zt to z1, in terms of the sensor model and the previous belief bar. Yeah. So if you remember Bayes' rule, right? So what we want to do is we want to let's see how can we write this? We can write this as p of xt comma zt given u1 to ut and z1 to zt minus 1, right? Divided by, or sorry, there's not a lot of space. Give me a second. So you wanted p of xt given c1 to zt and u1 to ut. Okay? This is what the belief that we want. We can write this by, you can think of Bayes' rule. You have p of x given y is p of y given x times p of x by p of y. right? That's what Bayes rule is. Now you can do a little bit of pattern matching, right? So we want a P of X given Y, and our Y is going to be ZT, right? And our X is going to be XT, right? And so you can write this as, so you can think of this as Bayes rule, right? So you want Bayes rule where your X variable is XT, your Y variable is ZT, right? And so you can write this as P of ZT given XT and Z1 to ZT minus 1, U1 to UT minus 1, right? Times P of XT given Z1 to ZT minus 1 and U1 to UT minus 1, right? Divided by P of Y, right? Which is, let's write this, let's skip it for now because it's going to be a little bit hard to fit in here, right? But let's see what we did here. We just did pattern matching, right? So we said that's Bayes rule. That's a Bayes rule says P of X given Y is P of Y given X times P of X divided by P of Y. Okay? It's Bayes rule. And now we just did pattern matching. We want this to be X, we want this to be Y, and everything else is just background information. So it's always going to remain on the right side of the column. Yeah. It's like common across everything. Okay? It's just background information. And so you want to say, let's just use Bayes rule, but just replace X with XT and Y with CT. Yes. And so what we've done here is this is the P of Y given X term, right? So Y is ZT and X is XT, right? And this is the P of X term, right? So because X is XT, right? And everything else is background information, right? And so all we did is Bayes rule, and then if you want to have the denominator is basically going to be the sum over okay. It's going to be the sum over ZT given XT. It's going to be basically, let's call this entity blah, right? It's just going to be the sum of blah over ZT, right? It's going to be the sum of blah over XT. So it's going to be the sum of blah over XT, which is going to be that, right? So what we've done is we've used Bayes rule, right? And we said XT is going to be X, ZT is going to be Y. We just substituted things in, and we get this product of two terms, right? Does that make sense? I know that wasn't as clean as I'd like on this page, but all we're trying to say is that what we want to do is we want to incorporate the measurement. We're just going to try and use Bayes rule to do so. Yeah. Now, the important thing to remember here is that the first term is also subject to the Markov assumption, right? So if you go back to our previous thing, we saw that the current measurement is only dependent on the current state, right? Which means that like all of this dependence goes away, right? The current measurement is fully dependent on the current state. So it's independent of the entire past. Yeah. So this term is just going to become P of ZT given XT. Right? And then the second term, if you notice, is just belief bar. Right? So the second term is just belief bar. And so what it means is that your numerator just becomes P of ZT given XT times belief bar of XT. And then you have like this normalizing factor, which is the sum of P of ZT given XT times belief bar over XT. Right? So all we did is we used Bayes rule. We use the Markov property that the sensor reading is only dependent on the current state. And then we notice that the second term in the Bayes rule is belief bar, right? And so you can write the current belief is taking in the previous belief bar after the motion model and the sensor model, and then normalizing it. Right? Does that make sense? So let's think about what this means intuitively, right? So it's saying that belief bar was telling me where I think I might be before I take a measurement. Then the motion model, P of zt, or the sensor model, P of zt given xt, tells me how likely it was that I got the sensor reading at that particular state, right? So at some state xt, how likely was that I got some zt? And so I'm going to take every point in my belief. I'm going to weight it by how likely it was that that thing produced that sensor that I actually got. And then I'm going to renormalize. So it's just saying, I want to take my sensor reading. The sensor reading is going to tell me how likely it is that my belief was correct. And I just need to normalize it because it's a probability distribution. Right? So the way to go from belief bar to the next time step belief is just take the belief bar, multiply by the sensor model, and then renormalize. Right? And the renormalization is just like making sure that the scale is correct. That's it. That makes sense? Are we following that? Ask me any difficult questions you might have, or I can rederive it again if that wasn't clear. No problem. Do we feel good about that? Okay, sweet. Okay, so let's kind of recap. Okay. My iPad skills are not good. I will do this in a second, sorry. Okay, so to recap, we are going to apply this process over and over and over every time, right? So we started with some initial belief, right? Let's say I kind of guessed where I was in the world, right? I took one action. First thing I'm going to do is do the prediction step, which is taking the previous belief, which is initialized to something, push it through my dynamics model, my motion model, my transition model, right? Which is telling me how the world changes. And you sum it up over all the places I could have been in the past, right? That's your predictions. That gives you belief bar. And then you take a measurement, and to incorporate the measurement, you take your belief bar, you multiply it by the likelihood that that sensor reading was produced, and then you renormalize, right? And so essentially what you're trying to do is you're just trying to, repeat this process over and over and over. So like every step of your filter, your Bayesian filter, you're just going to run this two-step process, right? Prediction, correction, prediction, correction, prediction. That's it. Does that make sense? Yeah.
What is that Greek letter that was?
Oh, the eta. The eta is just that normalizing factor, right? So it's essentially it's just trying to make sure that you're a proper probability distribution. And so it's saying that, okay, your numerator, right, was your belief bar xt, and this is just going to sum this up over all the xt's, right? Okay. So do we feel more confident about Bayesian filtering now? Do we want to go through an example, or should we go to the stuff I was supposed to do today? You should tell me. It's your class.
You mean like you say an example like an application?
Like we could run through one like concrete example with numbers to understand how exactly Bayesian filtering works. Would that be helpful?
Yeah.
No? Yes? Show of hands. Would that be helpful? Raise your hands. All right. Seems like it. Great. Okay. So here's the example that we clicked on. But basically, it's trying to estimate whether a door is open or closed. Yeah. So it's trying to say you have a robot, it's trying to open a particular door, right? So the state of the world is open or closed. There's two actions, to pull or to leave, right? And then there's two sensor measurements. You have some sensor that's telling you like, is the door open or closed, right? So the entire system is that the state of the world is either open or closed. You have some actions that are pull and leave, PNL, and then you have some sensor measurement, which is noisy, it's not accurate, but it's telling me, okay, I think the door is open, or I think the door is closed, right? And that's our system. So we can think of our system as having the sensor measurement given P is ZT given XT, and a transition model, which is telling me what is the likelihood things would be open if I applied pull, or what is the likelihood things would be closed if I applied pull, and so on, right? So the model of my world, right, is you can break it up into two things, right? The first model is telling me, I was at state C. Yeah, I applied the action P, and the likelihood of it being open at that point is 0.7. And so it makes sense. You're closed and you apply the action P. Your not going to succeed with 100% likelihood, so it's going to be 0.7 successful. You're at closed, you apply P, and you're going to be 0.3 unsuccessful, right? And so that's your transition model, and you do this for both actions, right? So you're going to say, you can construct a matrix, right? So the matrix is saying, let's go through the matrix one term at a time, right? So the top left is saying, if I was open and I applied the action pull, right? Then I would be open with 0.8, right? And if I was closed and I applied the action pull, then I would be open with 0.7, right? And if I was open and I applied the action pull, I would be closed with 0.2, and then you complete the square, right? So that's describing how the world will work, and the same for leave, right? So for leave, it's saying that, if you're, maybe this column is the most informative, but say if you're already closed, right, and you applied leave, the likelihood that you're going to be open is very little, right? And so it's like, that kind of describes how your world works. So that's going to be our motion model, our transition model, right? So it's going to be that P of xt given xt minus 1 ut, like that's this thing, right? It's a P of xt given xt minus 1 ut, right? Just instantiate for two different u's. Okay. And this is our measurement model, right? So our measurement model is saying that if my state was, if the observation that I got was open, right? So it's a little bit confusing because the state and the ZRO, right? But what this is saying is that if my observation that I got was O, then like the likelihood that I would get it if my state was open is 0.6, and the likelihood that I'd get it if my state was closed is 0.2, right? And the same for if the measurement I got was C, likelihood I would get it if the state was open is 0.4, likelihood I'd get it if the state is closed is 0.2, right? So this is defining this P of ZT given X, right? Everyone follow the system? Yes? Okay, sweet. So now let's start from our initial belief. I'm not very certain if the door is open or closed. I have 0.4 belief that it's open, 0.6 belief that it's closed, right? And that's where I think the state of the world is. And now I want to take an action and see what happens next, right? So I'm going to take the action of pull, right? And then I want to figure out what my belief is, or my belief bar is after I take pull, right? We haven't taken a measurement yet. We've just taken an action. Okay, so what we want to do is we want to figure out belief bar. Belief bar is the previous belief times the transition model summed up over the previous states. Right? So this is our transition model, right? This thing. This is our previous belief. We're gonna multiply those and then sum those up. Okay? So let's try and work through the steps. But does that make sense? We're just trying to work out belief bar. So we're saying that, okay, our previous belief was 0.4 open, 0.6 closed, right? Our transition says, this is the likelihood you transition to open, this is the likelihood you transition to, this likelihood you transition to open if you were open, this is the likelihood you transition to open if you were closed, right? And vice versa. And so you can just multiply these two matrices, right? And so when you multiply these two matrices, what do? You multiply this thing times this thing times this thing, right? So 0.8 times 0.4, 0.32, 0.7 times 0.6 is 0.42, right? And so what would we get? You all fill it in. What's the belief bar going to be? Oh, is it already filled in? Jesus Christ. Okay, but it's going to be 0.74 and 0.26. But this intuitively makes sense, right? It's like, this was where I thought I was going to be. And then I took the action of opening the door, which succeeds more likely than not. And so my belief is now that the door is open, right? Or like, my belief is more towards the door being open. So that's why this number is higher than this. Right? Does that make sense? Okay. And now I'm going to take a measurement, right? So I'm going to take a measurement, and the measurement is going to tell me, hey, I think this thing is closed, right? So now I need to incorporate that measurement to update my belief. So how am I going to do that? I'm going to take my measurement model, multiply it times my belief, and then renormalize it, right? So what is this going to be? Let's see. You had 0.74 and 0.26. Right? Those are my belief bars. And then I multiply it times my sensor model, right? And so my sensor model says that the sensor, the likelihood that you got the reading closed is 0.4 if it is open and 0.8 if it is closed, right? And so you're going to multiply those and then renormalize, right? So you're going to multiply this is going to give you 296, this is going to give you 208, and then you're going to renormalize those till they sum to 1, because your belief is a probability has to sum to 1. Okay? And so that's going to give you this belief. But again, it intuitively makes sense. You thought it was open, the sensor told you that it's closed, so your likelihood of it being open is lower, right? And so now after your next step of Bayesian filtering, you've said, okay, my likelihood of it being open is 0.58, closed is 0.42, and you repeat, right? So what did we do? We started from an initial belief. We took pull, we did the motion model step, it gave us a belief bar, and then we took the correction step, it gave us a belief. Our belief is more accurate. Okay, do you feel good about that? Yes.
In the motion model step, when we had
Yeah.
that transition matrix,
Right.
is that something that's like predefined by the user, or is that something that's like found?
Yeah, that's a good question. So usually, in a lot of these systems that we're going to consider, since we're model-based, like when I talked about the world model a couple lectures ago, that's your world model. So that's telling you how the world is transitioning. So that's usually going to come from a user or from a domain expert with some tuning of parameters that you do by hand or through some autonomous procedure. But we're going to assume it's known. In the end of lecture, we're going to talk about systems where it's not known and you get it from data. Yeah. But for the first part of the thing, we're going to, like in all your homeworks 1, 2, 3, you're going to assume that that is known, but wrong. How are we doing on time? Yeah. Sorry. Okay, so that was Bayesian filtering, right? Okay, so we feel good about Bayesian filtering, or all right, sweet. Let's see what we can cover in 10 minutes. Where was I? Okay, so what I'm going to talk about today, or the rest of 10 minutes of today, is going to be basically, okay, we did all this Bayesian filtering stuff. That's great. But as, what's your name again? Samir. As Samir was just saying, how do we get these things, right? And how do we get the sensor models? How do we get the motion models, especially for a race car, right? So what we're going to try and do in the rest of the time is we're going to try and instantiate a concrete version of these motion models and sensor models for a race car, right? And so essentially, the idea is we want to figure out what exactly these things are, just like abstract quantities right now, right? I want to tell you what they are exactly for a race car. Yeah. Okay, so in the context of the car, it's going to say, okay, like your action is your velocity and your heading. You're going with some current position and some current heading angle. You applied some velocity, you applied some steering angle. Where is it going to be next, right? And the same way, you're going to apply your LiDAR. Your LiDAR is going to give you some readings in different directions. And then you want to apply that to figure out where you are in the world. Right? So we're going to try to do Bayesian filtering first to understand where the car is in the world. And so the car doesn't know where it is. Drop it in the world. It's going to move around, and it's going to move around to figure out where it is. And then you can do control and all the fancy things on top of it. But the first step is figuring out where it is. Okay, so why is this not like stupid easy? Like, how would you do this? You all know how race cars work, right? Kind of. What makes this hard? Or is this not hard? Do we just need to go through the next 5 slides? What do you think? Yes.
I guess you have to depend on the sensors and that the sensors are correct.
Right. So you have to be probabilistic. That's what makes it hard, right? You have to figure out how to incorporate noise into the whole process, because your models are almost always going to be wrong. Unless you've modeled, the intricacies of every single inch of the floor and it's constant, it's going to be wrong, right? And so both your correction model and your prediction model are going to be wrong. Your LiDAR is going to be wrong. Your motion model is going to be wrong. Your wheels may slip. Your friction may change. So you have to incorporate them with noise, right? And that's what's going to make it tricky. right? So what we're going to do is we're going to do physics, and then we're going to add some noise to the physics, and that's going to tell us how to do our motion model. And the same thing for the sensor model. You're going to do something that looks like physics and add some noise to it, right? And so, depending on how much time you want to spend, you can have more or less accurate models. So like in F1 racing and things like that, they want to be extremely accurate. So they spend a ton of time modeling the cars exactly, modeling how they drift and how they slip and everything like that. And so you have extremely high fidelity models. Right? When we have a high fidelity model, your noise is going to be lower. But we're in a race car, it's not like high stakes. And so what we're going to do is we're going to try and do really simple models. Like we're going to make a lot of simplifying assumptions. But when you have a simplified assumption, the model is going to be wrong, right? And so you have to deal with the incorrectness of your model with noise. And so the important thing we're going to do is the choice we're going to make is not to have high fidelity model, to have a simple model to make everything computationally tractable, but we have to compensate with noise, right? So the Red Bull simulator would tell you exactly where you are. Our simulator is going to say, you're like kind of somewhere. Okay? If you guys want to make a Red Bull simulator, you should. Extra credit. But for now, we're going to do the simple thing, right? And so kind of based on what I was talking about last time, we're going to have these equations of motion. We're going to have physics. The physics are going to be wrong. And then we're going to try and, take all of the mistakes we made in our modeling, and we're going to stuff it into this noise, right? So we're going to say, okay, we got the friction wrong, we got the slip wrong, we got the actuation error wrong, we got lots of stuff wrong. But we're going to compensate for all of it by accounting for the fact that the model is wrong. So we're going to maintain uncertainty, right? And that's like the lesson to take away is that you want to be probabilistic so you can account for the fact that models are wrong all the time, right? So even if you're doing machine learning, your models are going to be wrong. You want to be probabilistic so you can account for the models being wrong. Yeah. So the key idea is you want to account for all the things that are wrong. So you want to make sure that you can deal with what things are unknown. You want to make sure that it's computationally cheap because you're running a car at high speed, right? And you want to be able to explain any measurements or motion that you have. So you want your model to be accurate enough to do control, but it doesn't need to be correct. That's the main point. Right. And so the type of model we're going to study is a kinematic model, not a dynamic model. So a dynamic model is something that deals with forces, right? So Newton's law says F is equal to ma. You're dealing with forces and dealing with accelerations, right? We're going to deal with kinematic models, which tell you how do speeds map into positions, right? And we're going to assume that something else is going to help us deal with forces. And we'll cover that in the next part of the class. But our actions are going to be something like telling us what velocities our system is going to go at. And what we're going to figure out is how does that change position, right? And so what we're going to do for state estimation is our actions will be our U's, are going to be velocities and steering angles. And we're going to try and figure out how that changes position, but we're not going to worry about what currents went into the wheels, and we're not going to worry about the low-level stuff. We'll worry about that in early February. Okay? Does that make sense? Let's abstract things away for now. Just deal with, okay, I was here, I applied some velocity, and I applied some steering angle. Where does the car move? And essentially, the model is going to try and represent this as your state, right? So your state is, where are you in the world? What is your x coordinate? What is your y coordinate and your heading, right? So if you think of your race car, right, you have, where you are in the world, x and y, and like, what is your angle, right? So your angle is like, what is your angle with some axis, right? Some canonical axis. So the state of the world is going to be x coordinate, y coordinate, heading, and your actions are going to be your speed and your steering angle, right? So in your race car, your actions will be your speed, right? And your steering angle, let's say. So you're going to rotate your wheels by some amount, you're going to have some speed, you're going to have some steering angle, and that is going to be your action. Then what we're going to figure out is how do we predict how this thing changes when we apply a particular velocity and steering angle. Yes? All right. And to learn that, you will have to come to class on Friday, and we will go through that. All right. Thank you.
You asked me to come see you. at
Yes,
the sites.
I will add you to one of the teams that are existing. But really nothing major has happened. We just assigned teams. You should just meet up with your team and first homework doesn't really need the card. So you could just meet up with them and if you could send me a picture of your ID. I need to get you card key access to the.
Oh, okay. Awesome.
It's
All right.
in
Yeah,
Allen School basement and
22.
22.
Okay.
Cool. All right.
All right, I'll
Yeah.
send that to you later.
Welcome to the class. Hopefully it's
thank
fun.
you. Oh, yeah, it'll be fun.
All right.
Do you want me to send that to you on Ed? Is that okay? Or do you want me
Just
to
do it on email.
Email? Okay.
All right. Cool. All right.
Thank you.
Yeah. Hey.
For belief to belief part,
Yes.
you remind me where the denominator goes.
Ah, yes. Belief bar to belief or belief to belief bar?
Belief to belief part. So for here, I remember there are some.
No, that's belief bar to belief, right?
Oh, yeah.
Let's step outside and I will work through it with you inside, just so the next class can teach. Hey, sorry.
Sorry, we'll introduce class last
Okay.
night. My friend told me they already assigned to different groups.
Yeah, can you email me with your name ID
Okay.
and I'll assign you to a team.
Okay,
And
thank you.
yeah, email me on my cs.washington email
Okay,
and I'll check that one. Yeah.
thank you.
Sorry, give me 1 second.